So, good evening, everyone. Welcome to the 11th live session for the course Concrete Technology offered by NPTEL. I am Arshit Agrawal, a PMRF PhD scholar from the Department of Civil Engineering, IIT Bombay, and I will be conducting weekly live session for the course for the entire course duration. So first of all, for those who have joined for the first time, so these are weekly interactive sessions that are held every Tuesday from 6 p.m. to 8 p.m. During the session, we interact by answering to the questions in the chat box, by posting the questions in the chat box, or by raising hand, unmuting, and asking the queries. Apart from the course, you can always use the discussion forum of the course, where you can ask your doubts, which I will be addressed there itself or in the next session. And attending these sessions regularly will help you to answer the graded assignments easily and will help you to further understand complex topics holistically. So in today's session, we will first revisit the last live session that was for the week 10 content, just a quick recap, and then we'll move into the things that are covered in the week 11 content. Okay, so week 11 content that we'll discuss today will continue our discussion on the durability of concrete by discussing about corrosion. So for this session, the session is divided into following sections. First, we'll talk about chloride induced corrosion, then, we'll talk about science behind corrosion, then, we'll move into corrosion protection method, what is the role of concrete in mitigating corrosion, and finally, we'll have a overview of special purpose concrete. In between, there will be some objective and numerical questions, like around 20 questions in total, that will help to challenge your understanding about the concept. And finally, we'll conclude the discussion and I will try to address any other queries post discussion. So last week we started discussing about durability of concrete, where we first talked about what does durability mean as per ACI and IS provisions. We understood that durability of concrete is affected by two factors. First is the concrete system and second is the aggressiveness of the environment, where concrete system governs the quality of concrete while environment defines the degradation of concrete. In IS code, we understood how degradation influences the service life and then how repair, rehabilitation, and retrofitting can improve the service life. Going one step further, we understood what each of these three R's, that is, repair, retrofitting, and rehabilitation, means in terms of their role in enhancing the durability of concrete. Then, coming back to the course content again, we define different ways in which degradation can happen in concrete, which can be classified into six divisions: mechanical degradation, physical degradation, structural degradation, attack, biological degradation, and corrosion. So in this we talked in detail about chemical degradation, where we discussed about sulfate attack, both internal and external. We talked about in that we also talked about delayed ettringite formation. We talked about acid attack. We talked about alkali aggregate reaction, where we saw both alkali silica reaction and alkali carbonate reaction. And finally we talked about frost action, or what we say freeze thaw action. Then we started discussing about corrosion in detail, where we first defined corrosion in a three-part definition, connecting the cause of corrosion based on thermodynamics and rate of corrosion based on kinetics, with the effect of corrosion in terms of degradation. We saw how corrosion damage is classified into different stages and how concrete behaves in these different stages. So in the second figure you can see there are three stages in which corrosion damage is classified, and in the first figure you can see how in different stages the concrete will behave and how the repair cost will increase if the action against corrosion is delayed. Now, in terms of depassivation of steel reinforcement, we talked about direct and indirect effect. Direct effect means when the aggressive ions directly affects the steel and not concrete, which is the case of chloride induced corrosion. And indirect effect means when aggressive ions affects the concrete and then the effect on concrete causes depassivation of steel, which is the case of carbonation corrosion. So, we discussed in detail about carbonation corrosion, what is carbonation, how it causes corrosion, what type of corrosion it causes, how carbonation can be detected, and how the carbonation depth is modeled in concrete based on square root of time law. Okay, so now the next thing in reinforcement corrosion is chloride induced corrosion. So now this chloride induced corrosion in concrete is a very frequent cause of corrosion in reinforcement steel. Okay, but from where chloride can come? So sources of chloride can be seawater if the structure is present near a seashore. It can be soil or groundwater. There can be de-icing salts, which can be a source of chloride intrusion in concrete, and there can be contamination of chlorides in cement, aggregate, and mixing water. So these are the most common sources of chloride from where chloride ions can enter the concrete. Now, if we see transport of chlorides through concrete for corrosion, this transport step is divided into two processes. First is the initiation and the propagation. Okay, so you can see here in this graph, till this point it is initiation, and then till this point it is propagation. Okay, so this initiation that is defined from the start to this point, it is the time period in which a certain amount of chloride reaches the interface inside reinforcement and concrete. Okay, so you can see in this figure, this is my reinforced concrete. Okay, and there is reinforcement inside at present at a cover depth D. Now chlorides will start to ingress from the surface of concrete. Okay, so the time taken by chloride to move from the surface of the concrete to reach the steel reinforcement in a certain minimum amount, this time period is known as initiation period. Okay, and this certain minimum amount which is needed for chloride to cause depassivation of steel is known as critical chloride threshold. Now, why this certain chloride amount is needed? Because initially there is a passive layer over the steel reinforcement, and to break passive layer, certain chloride concentration is needed, whose value will depend upon two things: what the material used for reinforcement and the pH of concrete. Okay, so this movement of chloride through concrete is happens by a process known as diffusion. Okay, which is based on concentration gradient. So outside there is a high concentration of chloride, inside there is a low concentration of chloride. So what will happen? Chloride will move from higher concentration to a lower concentration due to diffusion, and the rate at which this chloride is moving, it is defined as diffusion coefficient, which is represented as dCl. Okay, so here you can see there are four parameters. D was the depth, ClTH is the critical chloride concentration at the interface that is needed. DCl is the rate at which the chloride is diffusing through the concrete, and CS is the amount of chloride present on the surface. Okay, so and once the corrosion is initiated, what will happen? Due to rusting, micro cracking will happen inside the concrete. When these cracks will connect, they will form a macro crack, and finally it will lead to spalling or delamination of concrete. And at after a certain time, what will happen? A certain allowable damage level will be reached, and will say that the service life of concrete has ended. Okay, so this point here, this is known as the maximum allowable damage level. Okay, so if that damage level is reached, we say that the concrete has lost its service life, and this is how chloride causes corrosion in concrete. Okay, so if we see the zoomed image of this initiation period, okay, so initiation period we have understood right now, it is dependent upon four entities. First is the surface chloride concentration, second is the covered depth, third is the diffusion coefficient, and fourth is the critical chloride threshold. Okay, so how does these all four parameters is determined? So surface chloride concentration, it depends upon the exposure condition. So if my structure is present near the seashore, it will have a higher surface chloride concentration. If my structure is far away from the seashore, it will have a lower surface chloride concentration. Critical chloride threshold, as we said earlier, it is a property of steel concrete interface which depends upon the reinforcement type that we are using. as well as on the pH of concrete. Okay, because higher is the pH, stronger is the passivation, lower is the pH, weaker is the passivation. Okay, so if there is weak passive layer, then the critical clear threshold will be low, so it can initiate corrosion early. Then third is the cover depth, which is a design parameter. It can change from beam, column, slab. And fourth is the ion diffusion coefficient, the rate at which the chlorides will move through concrete, which is determined experimentally. Okay, so here you can see at the bottom, depassivation takes place when chloride reaches a critical value at the rebar, which depends upon the cement and the steel type. So you can say cement paste, because that is what will govern the pH of concrete. Now, for estimating diffusion coefficient of chlorides, the ingress that defines the ingress of chloride ions through concrete, it is modeled using Fick's second law of diffusion. Okay, so to calculate diffusion coefficient, we use Fick's second law of diffusion. Okay, which is used for non-steady state diffusion processes. Okay, so basic Fick's second law is written like this: d del c by del t is equal to dcl times del 2c by del x square. Okay, so you can see here in this figure, it represents a simple concrete system. Okay, so this is my concrete and this is my surrounding, which is of a semi infinite length, and they which is rich in chloride. Okay, now due to high chloride concentration at the surface and very low or zero chloride concentration inside the concrete, what will happen? Diffusion will happen in this direction. Okay, now this is a second order differential equation. So to solve this differential equation, we need some boundary conditions. Okay, so first condition is, it is assumed that concrete is a semi infinite homogeneous medium. So here there is an end, but here it is infinite. Okay, so that's a semi infinite homogeneous medium. So we consider concrete as a homogeneous material, and this surrounding is spanning in this direction till infinity. So there is no loss in surface chloride concentration that will happen at any time. It is abundant at the surface. Whatever concentration we are assuming, it will be abundant at the surface. Okay, so using this semi-infinite concentration boundary condition, and knowing that at x is equal to 0, so this is my cover depth, x is equal to d, and this is my surface where x is equal to 0. Okay, so at depth equal to 0, my chloride concentration is Cs, and at depth equal to D, my chloride concentration is Ci. Ci is like initially whatever chloride is there in the system in my concrete due to the presence of chloride in water, cement, or aggregate. Okay, so when I apply these two boundary condition and I assume that it is a semi-infinite homogeneous medium, this differential equation, it will be resolved into this equation, where Cxt defines chloride present at any depth x after any time t. It is equal to Cs minus Ci times error function of x to the x upon 2 into under root of dcl into t. So after a time t at a certain depth x, what chloride concentration is there, we can estimate using this equation. Okay, so here I have used two condition: x is equal to 0, cxt will be equal to cs, and x is equal to d, time is equal to 0, cxt is c of x comma d, c of d comma 0 is equal to ci. Okay, so using these two boundary conditions, we have come up with this solution. Now you can see, are all four parameters are there in the in this equation that we defined earlier: cs, cx, clth, d, and dcl. So when this value will reach the critical chloride, and my will be equal to d, and I know the surface chloride concentration and know the initial chloride concentration in the system, what I can do, I can rearrange this equation so that I can take my time on the LHS and all other terms on the RHS. So if I do this rearrangement, what will happen? I will get the service life of my concrete. If I assume that propagation period is negligible and just the initiation will define the end of service life. So this time T for corrosion to initiate at the reinforcement surface, we can determine if we know the DCl value, the cover depth, the surface chloride concentration, and the critical chloride threshold. Okay, so with this we can estimate the service life of reinforced concrete under chloride induced corrosion. Now, how this is done in lab, like how we can estimate this DCl value in lab, because all other values will know the cover depth, the surface chloride concentration, and the critical chloride threshold we will know initially. But how to estimate the diffusion coefficient? So in lab we use bulk diffusion model, which is based on ASTM C1585 for estimating that diffusion coefficient of concrete. Okay, so you can see in this what is done. This is my concrete cylinder of diameter 150 mm and height 300 mm. Okay, so we prepare a concrete cylinder and we coat the curved side of the concrete cylinder with the epoxy coating so that we can simulate a 1D diffusion of chloride. Okay, now this concrete that I have coated, I will keep it in ponding. Okay, so this is a pond which is rich in chloride. Okay, so in this ponding, I have kept my concrete. So what will happen? This surface also I will coat. Okay, so what will happen? Initially, there will be some concentration inside Ci, and at the surface, there is Cs, which is higher concentration. So what will happen? Chloride will diffuse through concrete. So as chloride will diffuse after as per ASTM's code, after 35 days of this ponding, what we do, we take the concrete out and I will drill the concrete. So I will using a rotatory drill. What I will do, I will drill the concrete and I will collect concrete powder from different depths. Okay, and then at from these concrete powder I will estimate the chloride content using titration analysis. Okay, so titration analysis is done to calculate how much chloride is there in the powder that we have collected, and that chloride concentration versus depth is plotted, and this curve that you see, it is known as non-steady state diffusion. So if it would have been a steady state, it would have been a straight line. Right now it is a curved line, so this is a non-steady state diffusion. So using this curve, on this curve I will fit the fixed second law. Okay, so this equation that we have derived here, okay, I will fit that equation on this curve and then I will get the DCl value. How? Because I know the time t, I know the depth x for each cxt, I know the surface chloride, and I know the initial chloride. So everything I know, so I will get the DCl value. Okay, so this is how diffusion chloride is determined in laboratory condition for a particular concrete. Okay, now how concrete will influence the diffusion coefficient value? It can influence in two ways. First is the permeability of concrete. So denser is the concrete, lower will be the rate of chloride ingress, and so lower will be the diffusion coefficient. Okay, so if I have a very dense concrete, what will happen? Chloride won't be able to easily penetrate through the concrete. If it won't be able to easily penetrate, then the diffusion coefficient value will also be lower for chloride. And second is the chloride binding ability. So it is not like concrete is not interacting with chlorides. Concrete can interact with chloride. There are certain cement phases that can interact with chloride. How? So CSH that is there inside concrete, it has the ability to physically absorb chloride ions. Okay, so on the surface of CSH, chloride ions can get physically absorbed while they are diffusing through concrete. While aluminate phases like C3 and CH, they have the ability to chemically absorb chloride ions in the form of Riddle salt and Kugel salt. So these three phases that are there in my cement hydration. So CH and CSH, this is after hydration, and C3 is like leftover C3 which is not been hydrated. If these are present inside my concrete system, they can interact with chloride while chloride is diffusing through the concrete, and they can delay the diffusion of chloride, or they can decrease the diffusion coefficient of chloride. So these are the two parameters which can affect the diffusion of chlorides through concrete. Now, this figure shows some of my experimental data on different binder composition concrete and how their DCl value is found to evolve over time. So this we talked about different concrete, like between two different concretes. In the same concrete, if I will increase the curing gauge, what will happen? The porosity of my concrete will reduce as it will undergo further hydration. So then also this diffusion coefficient value will decrease. So you can see here, for 100% OPC concrete, from 28 days to 365 days, you can see the DCL value has continuously decreased. Why? Because my hydration of concrete has become dominant in controlling the rate of diffusion. However, if you see, instead of OPC, I will add fly ash in 25% replacement, or slag in 40%, or silica fume in 8%, or ultrafine slag in 10%, or ultrafine fly ash in 7.5%. So initially you won't see much difference from OPC at 20 days, because these are all pozzolanic material. They take time to show reactivity. Okay. However, after 365 days, if you compare the diffusion coefficient value of a OPC based concrete and a supplementary cementitious material added concrete, you can see they show a very low value compared to OPC. So OPC, it was showing a diffusion coefficient value of 6.07 into 10 to the power minus 12 meters square per second. But a system like slag or silica fume or fly ash, it can show a value up till 2 to 3, 2.5 to 3, which is almost more half of what OPC was showing. Okay, so this can be the effect of, this is how significant my cement composition or the use of mineral admixture can be in enhancing the durability of concrete against chloride diffusion. Okay, and lower is the diffusion rate, more time chlorides will take to reach the steel surface, so higher will be the service life of my concrete. Now, once I have estimated the diffusion coefficient value, we can have a check for the surface concentration. Again, either by using like titration method. So, like in this figure, we saw how we drill from different depth and collect concrete sample. Now, so suppose I am drilling from at the surface only, very near to the surface, and I am estimating the chloride value. So that will be nothing but my surface chloride concentration. This we can do, or we can take some predefined values which are present in code. So you can see these values that I have mentioned here in splash zone or near shoreline or 1 kilometer away from shoreline, how the surface chloride concentration is changing. This value I have taken from Japanese standard. Okay, so either we can use some standard or we can do our own estimation of surface chloride concentration. Okay, so once we know the surface chloride concentration, we know the diffusion coefficient value, we know the cover depth, and we know the critical chloride threshold. Okay, so generally as per IS code, critical chloride threshold is taken as zero point 0.6 kg per meter square. Okay, so meter cube. Okay, so if we know all these values, what we can do, we can estimate the initiation time of corrosion. Okay, so here you see I have written probability of initiation versus exposure period. Why probability? Because you can see this here, the diffusion coefficient value that we are estimating, it is not an uh, exact value. It comes with its own standard deviation, because we are fitting an experimental data on a mathematical equation, so that fit may not happen accurately every time. So that's why there is always certain uh, standard deviation associated with most of these parameter. Like surface chloride concentration can also have standard deviation, diffusion coefficient value can also have some standard deviation, see critical chloride threshold can also have some standard deviation, and cover, even cover, suppose I am designing a concrete for a cover depth of 50 mm, it may not be 50 mm every time, it may vary from 45 mm to 55 mm. So every data here has some standard deviation. So whatever t that I am predicting using this equation here, service life, it may not give me a exact value either. So instead of reporting a deterministic value, I can report, it is better to report a probabilistic value. So this curve here shows the probability. Okay, so where all standard deviation is taken into account. Okay, so this figure you can see what is the probability of initiation to occur, that we have written with exposure period. Okay, so for this figure I have prepared using MATLAB code for probabilistic service life estimation. And if I assume that 50% probability of failure is critical, so I can compare these different concrete types in terms of their initiation period. So you can see here, a OPC based concrete may give only 21.6 years of service life under this atmospheric condition. However, A slag based concrete can give more than double the service life under the same condition because of the denseness that the binder system is providing to the concrete and delaying the diffusion of chlorides through concrete. Okay, so this is how service life can be estimated if using for a chloride induced corrosion case. Now, just try to answer these three questions based on chloride corrosion. And in the meantime, if anyone has any doubt, they can ask me about the topic that we have discussed right now. Okay, does anyone has any doubt here? No doubts yet. Okay, so for the first question, what will be the answer? Which type of corrosion is mostly associated with chloride induced damage reinforcement concrete, reinforced concrete? Okay, any other answer? Okay, so for first question, the correct answer is B. Okay, so when we talk about chloride induced corrosion, it is the pitting corrosion that is happening. Now, what do we mean by this pitting corrosion? So, I will just give you a quick explanation. So, generally, there are two types of corrosion: uniform corrosion and localized corrosion. Okay, so what do you mean by uniform corrosion? Suppose this is my steel reinforcement, and if the corrosion is uniformly happening over the reinforcement surface, then we say the corrosion type is uniform corrosion, and this happens in case of carbonation induced corrosion. Why? Because carbonation depth is mostly going uniformly. Carbonation will mostly diffuse uniformly through the concrete, so depassivation will happen throughout the steel surface when it happens. So corrosion will happen throughout the steel surface. However, in case of chlorides, it is the permeation of chloride ions that is happening through the concrete pores. So there will be certain area over the reinforcement where chlorides will reach first in a certain minimum quantity. Now when chloride reaches here, the rest of the portion is still under passivation, but only this part where chloride has reached the steel reinforcement, it will depassivate. So what will happen, this will become my cathode and this will become my anode, and here the corrosion will start to happen, and here only it will continue to happen, so it will form a pit here. Okay, so such corrosion is known as localized corrosion. So there is a localized loss of steel reinforcement, and the corrosion is known as pitting corrosion in case of chloride induced damage. Okay, so when this uniform corrosion happens, what happens, the crack will appear easily on the surface. But when pitting corrosion happens, what will happen, you may not see cracking on the surface at very early ages, but internally my reinforcement is getting degraded. So this is more severe form of corrosion, okay, compared to carbonation corrosion. Okay, I hope everyone are clear with the explanation why it is pitting corrosion and what is pitting corrosion. For question number 2, what type of cement is most effective in reducing the chloride penetration in reinforced concrete? So can anyone tell me the answer? Okay, I have seen one answer. Can anyone else try? What will be the answer? Okay, so for the second question, the correct answer will be C. Portland pozzolana cement with fly ash. Okay, so right now we have seen a lot of cases which gives you the indication of this answer. You have seen all these cement types: fly ash, slag, silica, fume, ultrafine slag, ultrafine fly ash. They all are pozzolanic material. So what a pozzolanic material does, it consumes CH to form CSH, and it densifies the concrete system. If my concrete system is densified, what will happen? There will be less, the rate of diffusion of chloride ions will reduce through the concrete. Okay, so the correct answer will be Portland pozzolana cement with fly ash. For the third question, Why does the combined effect of carbonation and chloride attack significantly accelerate the reinforcement corrosion? So, can anyone tell me the answer? You have seen this discussion just one question ago. I have seen two answers. Can anyone else also try? Okay, so the correct answer for this third question is B. Okay, so what happens? Carbonation reduces the pH of concrete, and I have discussed this few slides ago that pH of concrete can directly affect the critical chloride threshold. So if the pH of concrete is low, the passive layer will be thinner. So there will be less chloride ions required to depassivate the steel reinforcement. So if there is carbonation, carbonation will reduce the pH of concrete and it will lower the chloride threshold for corrosion initiation. So lower is the threshold. It means that a little quantity of fluoride can also initiate the corrosion. Okay, so it can so carbonation will decrease the time for corrosion initiation. So this is how carbonation and chloride combined can significantly affect the accelerate the reinforcement corrosion. Okay, any doubt? What is the use of sulfate resisting cement? So sulfate resistant cement we have talked earlier to resist sulfate attack where there is no C3. If there is no C3, then there will be no ettringite formation, and ettringite formation is responsible for the expansive stresses that are generated inside concrete. Okay, just remember the last session where we talked about sulfate attack in concrete and remedial measures for that. Or you can also revisit the week 2 content. In week 2 content also, when we are discussing about aluminate hydration, we talked about attringite formation and we talked about the role of gypsum there and how it affects the sulfate attack. This exam thing we'll discuss at the end. Okay, right now let's first complete the course, the session. Okay, so let's move ahead. Now we have had a just a overview of what corrosion is, how corrosion is happening in concrete. But to understand corrosion better, to understand that thermodynamics and kinetics of corrosion better from a technical point of view, we'll discuss about the electrochemistry behind corrosion. Okay, now what do we mean by electrochemistry? So electrochemistry means that a chemical reaction or a group of chemical reaction is happening where electron movement is involved. Okay, so you have seen corrosion is a chemical reaction and there is movement of electron also that is happening in corrosion. So that's why I define corrosion as a electrochemical reaction. Okay, so in corrosion, there is interaction of metal with the environment, which is a electrochemical process, and it happens on the surface of metal. So at the interface of a metal, non-metal environment, this interaction happens, which is known as corrosion. So you can see here a basic equation how corrosion can be represented. Okay, so there is initially there's a metal A which is reacting with the non-metal B to form certain products, reaction products C and D. Okay, now suppose this is my metal Fe. So one of these uh, element A or B, it will get oxidized and the other one will get reduced. And this is what electrochemical reaction is all about. So it is a combination of corrosion is a combination of an oxidation and a reduction reaction. I have told you, na, just ask this question at the end. Right now, we are in the middle of a live session discussion. Or if you have any doubt regarding the exam, just mail the NPTEL team directly. They will tell you the exam date and everything. Okay. So I will again repeat what this reaction is about. So here A is a metal, B is a non-metal, which is my environment, and C and D are the reaction products. Okay, so in the product, one will be the oxidized form of metal, and other one will be the reduced form of non-metal. Okay, so if I convert this into a oxidation reduction reaction, this is something how the reaction will look like. So my metal, it is getting oxidized, and there is a non-metal which is getting reduced. Okay, so this defines corrosion as an electrochemical reaction. So oxidation, it happens at anode and results in release of electron. So when M is converting into M plus, it is releasing a electron behind. This is known as oxidation. Okay, and it is happening at anode. Okay, so for electrochemical reaction we define two electrodes, one is anode and one is cathode. Okay, and between these two, anode and cathode, there is charge movement that is happening. Okay, so this oxidation happens at anode, okay, which releases electron, while reduction happens at cathode, which consumes the electron that is released by the anodic reaction. So this electron that is released at anode, what will do, the cathode, the oxidizing species, it will consume the electron, it will consume this electron and form a reduced product. Okay, so this is how electron transfer is happening and the chemical changes due to change in due to a chemical reaction. So this is known as reduction reaction and it happens at cathode. Okay, now these reactions are charge transfer process that occurs across the interface of a metal and a aqueous solution or a non-metal, as we said earlier. Hence, they are dependent upon the interfacial potential that essentially corresponds to what is known as electrode potential. Okay, now what do we understand by the statement here? So, if you see the first figure, my iron is converting into Fe2 plus and it is leaving electrons behind. Now, what will happen? These electrons will move inside my metal to an adjacent site where oxygen from my non-metallic environment will consume these electrons in the presence of moisture to form hydroxide ions. And now in my environment, I have both positive ion and a negative ion. So what will happen? They both will react to form what is known as rust. Okay. So this is how metal and electrolyte are reacting to give to form corrosion. Now inside metal electron is moving and outside metal charge is moving. So if we see the second figure, between these two sides, the electron inside which will be moving from a negative terminal to a positive terminal. Okay, while the positive ion outside will move from a positive terminal to a negative terminal. So if we represent so here positive will represent a higher potential and negative will represent a lower potential. So we know this is basic from if you have read, you might have read this before. Electron moves from a lower potential to higher potential, while ions move from a positive ion will move from a higher potential to lower potential. So that is what we have said here. Okay, now for these movement to occur, there should be some potential difference that should be there in between these two sides that we have defined earlier. Okay, so if you see the second figure, between two sides, the for at the anode, the phi here represents the potential. So potential of metal at anode will be lower than the potential of metal at cathode. Okay, so if this is happening, then only the electrons will move from a lower potential to a higher potential. While in the solution, the potential of my solution at anode, it will be higher than the potential of my solution at cathode. Okay, so if this happens, this will be my positive, this will be my negative, so ions will move from positive to negative. Okay, so this is how movement of ion is occurring. Okay, and the difference between these two will be lower than the difference between these two. Okay, so if you subtract a smaller value from a bigger value, it will be always be lower. When you subtract a smaller value, if you subtract a bigger value from a smaller value, it will be lower than if you subtract a smaller value from a bigger value. So this difference between the potential of my metal and the surrounding, it is known as the electrode potential. And from this diagram we understood how this electrode potential will govern the flow of ions and the activity of corrosion. Okay, now measuring this electrode potential, the absolute value of this potential at an interface is not possible. Okay, so for recording potential, we report in terms of some standard electrode potential whose value we know. Okay, so like this E value that we have written here, which is represents the potential electrode potential of this interface, we can't directly report the C value. It is not possible to measure the potential here. So instead of this, what we do, we know there are certain systems whose absolute potential value we know. So relative to these certain systems, we report the potential value of our system, and these system whose potential value we know are known as standard electrode potential. Okay, one of the most commonly used standard electrode potential for understanding this concept is the standard hydrogen electrode, which is an electrode that scientists use for reference for all half cell potential reaction. Okay, by half cell I mean, so this reaction that is occurring here, it is one half cell, and this reaction that is occurring here is the second half cell. So half cell is like reaction occurring as cathode, is it is one reaction occurring at anode, it is one reaction. So both are different cells, both are half cell of a complete corrosion cell. Okay, so the standard hydrogen electrode, it is composed of 1 mole of H plus ion contained in a solid square piece of platinized platinum inside a tube, and during a reaction hydrogen gas is passed through the tube and the solution causes the reaction of hydrogen. So this is how the standard electrode hydrogen is made, and it is represented by this representation. Okay, this is a nursed representation, so we'll see later on how this is represented, and its absolute potential values is zero. So knowing this potential of this system, we generally estimate the potential of our system. Okay, apart from standard hydrogen electrode, there are other standard systems also, like copper sulfate half cell, mercury chloride half cell, and EgCl half cell, which are also used to calculate the standard potential of electrode potential of a corrosion system. Okay. Now in this table you can see with respect to standard hydrogen electrode, what are the values of different half cell reaction. So you can see this half cell reaction has a potential of plus 0.77 volt with respect to standard hydrogen reaction. Or if you see this reaction Fe2 plus consuming two electrons and converting into Fe, it has a negative potential with respect to standard hydrogen electrode, hydrogen ion hydrogen electrode. Okay, so in this way we can compute the absolute potential of each of the half cell if I know a standard potential value. Okay, now these potential value that we saw, they have two things to note about. First, they are the half cell reaction and not the complete cell reaction. So as I defined earlier, corrosion has two reaction, one is reduction and one is oxidation. Each of them is termed as one half cell reaction, which combines to form a one complete cell for corrosion. So first limitation is it is for a half cell. So whatever potential value that we have talked right now, this is for a half cell only, not for a complete cell. And second, the potential value that we have talked about here, it corresponds to some standard condition, like 1 molar concentration of iron on and fixed temperature. However, in reality, such condition may not be always be present. So, to calculate electrode potential in reality for a system, Nernst equation is used. Okay, so what is this Nernst equation? This Nernst equation is an equation which relates the capacity of an atom or an ion to take up one or more electron measured at any condition with respect to what is measured at standard condition. Okay, so suppose I have a reaction like this. A metal ion is consuming electrons and converting and reducing into metal. Okay, so for such reaction, Nernst equation is written like this. Okay, so electrode potential for reduction, it is equal to standard electrode potential minus 2.303 RT upon NF times log of product upon reactant. So this is like reaction coefficient that you may have learned earlier in earlier BTech courses or in 11 12. So how we write a activity coefficient for a reaction, the same thing we have written here. R is the constant, gas constant, T is the temperature, F is known as Faraday's constant, and N is the this charge, number of electrons that are present in the system. Okay, now how this equation came, so you can see this equation came from a reversible equilibrium reaction. Okay, so corrosion initially is an equilibrium reaction, so we can write the Gibbs free energy of the system like this: delta G is equal to delta G naught plus RT ln K. So K is the reaction coefficient, product upon reactant, and delta G is also related to minus NFE. So when we put these two equations here, we get the final relation. So if my delta G is negative, it says that the reaction is spontaneous, it can occur. If delta G is 0, then we say that the reaction is at equilibrium, and if delta G is greater than 0, then we say that the reaction is non-spontaneous. Okay, so this Gibbs free energy defines the spontaneity of the chemical reaction, and that's why we say potential is a thermodynamic parameter. Okay, now this reaction coefficients that we are seeing here, if these are pure solids, then the activity coefficient is taken as unity. For ions, activity coefficient is equivalent to concentration, and for gas, activity coefficient is equivalent to the gas pressure. And E naught reduction we can get from a standard reference electrode. Okay, so in this slide, I have just represented a complete kind of oxidation reduction half cell. So this is my metal A, which is getting oxidized into B, and there is hydrogen ion which is getting reduced into H2O. So for this reaction, the potential at the interface, how I will write, it will be oxidation at cathode minus reduction at anode. Okay, so for this, if I will write Nernst equation, so it will be represented like this: E naught minus 0.059. So this 0.059 factor came if I will take R as 8.314, T I will take 298 Kelvin, and F is 96485. So if I will take standard temperature condition, I will get 0.0559 as the factor. Okay, upon N is the number of charge which is involved in this transfer, so N will be equal to N only here, and log of product upon reactant. Okay, so this is for oxidation, and for reduction again I can write the similar equation for hydrogen ion. So this log of H plus concentration I can write as pH. So if I will take M here, so pH is nothing but minus log of H plus ion concentration. Okay, so that is what I have written here, and E naught will be 0 since it is a standard hydrogen reaction. Okay, H plus converting into H2O. So we have seen here H2 and H plus, it has a electrode potential of 0. Okay, so that's why this will be 0 here. So I can write my final electrode potential like this. Okay, so this is how Nernst equation is used to calculate the electrode potential of a interface, if I know both oxidation and the reduction reaction which is happening. Okay, now in reality, it is like at a metal interface, there is not just one reaction of oxidation or reduction that can happen. There can be multiple possibilities of oxidation reduction reactions that can happen. And what will happen here, it will be governed by like oxidation reaction will happen, what reduction reaction will happen, it will be governed by the pH of the system. So to tackle this, we have pore base diagram. So pore base diagram, it represents at different potential and at different pH what reaction can occur at a steel metal non-metal interface. Okay, so if we see this application of pore base diagram from nickel, so you can see there are different reactions that can happen. Okay, there are different equilibrium reaction that are present for a at a nickel surface. Okay, and if I write Nernst equation for each of these reactions, I will get different zones in which certain product will be stable. Okay, so in this way, pore base diagram is used to define the stability of a reaction product at different pH and potential. Okay. Similar application is there for iron also, which will become more complicated there since there are more possibilities of reaction to happen. Okay, so you can see here there can be several possibilities of reaction that can happen at the iron uh, oxygen surface. Okay, based on the pH of the system and the potential of the system. So at different pH potential, there are different stable products that can be found, which can be derived from pore base diagram. Okay. Now, how can we relate this pore base diagram to know the possibility of corrosion? So you can see in this diagram. Okay, if there is ions present, then we say that the system is corroding. If there is a certain oxide phases that are formed, then we say that the system is in passivation. And if there is just pure metal, then we say that the system is in stable state. So from pore base diagram, we can know where ions are forming, where oxidation products are forming, and where there is pure metal phase. So based on that, we can predict the possibility of corrosion to happen at a certain pH and potential. Suppose my potential of the system is zero point 0.4. Okay, so if my pH is 0.35, then I will say I am at the edge of corrosion passivation place. If my pH is lower than 0.35, then I will say that the system is in corroding state. And if my pH of the environment is more than 7 or more than 3.5, then I will say that the system is in passivation state. Okay, so this is how pore base diagram helps us to understand different behavior of a of a metal system based on pH and potential. Okay, now just try to answer a few questions related to this thermodynamics and potential part that we have discussed right now. And if you have any doubt in this part, you can ask me right now, because this will be something new for you and it is a little advanced form of discussion that that we are dealing with. So you are free to ask any questions that you want. Any part that you want me to repeat, you can ask. Any doubt in this part that we have discussed right now, like what is standard potential, what is electrode potential, and how this Nernst equation we have used to express this final expression, and what is pore base diagram. Any doubt in any part? Okay, so if there are no doubts, just try to answer these questions. So question number 4 says, which of the following factor does not affect the electrode potential of a half cell? Okay, so we have talked about electrode potential. Now, which of these following factors may not affect the electrode potential value? Can anyone tell me the answer? Okay, can anyone else try to guess the answer? Okay, I've just seen one answer. Okay, so for correct answer for question number 4 is D. Okay, why? So if you go back to this equation that we derived for electrode potential, so I will just copy this equation. So if you see this equation, of potential, electrode potential, it depends upon the ionic concentration, it depends upon the temperature, and if the species is gaseous, it can depend upon the pressure also. But nowhere there is molar mass of the electrode material that is coming into account. Okay, so that's why the correct answer is D. Now, question number 5, which of the following is true for the spontaneous electrochemical reaction at a certain standard condition? So, while I was talking about the derivation of Gibbs free energy and electrode, this equation, I have told this answer for this question. So, can anyone tell me what will be the answer for question number 5? What will be the answer? Okay, so the correct answer for question number 5 will be C. Okay, so E cell should be greater than 0 and delta G should be less than 0. So if you remember here this last equation that we talked about, okay, so we said that delta G is the Gibbs free energy, which represents the spontaneous nature of a reaction. So if delta G is less than 0, then we say it is a spontaneous reaction. One, for corrosion to occur, delta G should be less than 0 if I want corrosion to happen. Okay, and if delta G is less than 0, my E should be greater than 0. Okay, so for a spontaneous electrochemical reaction, E should be greater than 0 and delta G should be less than 0. Okay. Now, question number 6. Nernst equation for a generic half cell reaction is given by this equation. So, you know this equation, how it is written. Under what condition E will be equal to E naught? So, this right now it is E is equal to E naught minus 0.0059 by N times log of uh, this ion concentration to the ion concentration. Now, under what condition E will be equal to E naught? Okay, this is a very simple question, so just try to answer. Yes, Manoj, you can ask your doubt. Yes, yes, you can ask your doubt. In the meantime, I will tell the answer for question number 6. So you see, if this log of something becomes equal to 0, then what will happen? This whole term will become equal to 0, and then E will be equal to E naught. So we know log of 1 is equal to 0. So that's why the correct answer will be B. So when the concentration of the reactant is 1 molar, what will happen? This term will become equal to 0 since log 1 is 0. Okay. If n is equal to 1, nothing will happen. This term will remain the same. If E naught is equal to 0, then E will be equal to this term and not equal to E naught. And if E is negative, then also the answer won't be correct. Okay, so when the concentration of my reactant becomes equal to 1 molar, E will become equal to E naught. Okay, now try to answer these three questions related to pore base diagram quickly. Okay, Manoj. Just try to answer these three questions quickly. What does pore base diagram primarily represent? So while we were discussing pore base diagram of nickel and iron, I have told the answer for this question if someone remembers. Okay, so pore base diagram, the correct answer is B. So pore base diagram, it represents the stability of different oxidation state of an element as a function of pH and potential. So you can see here we talked about potential and pH and we talked about different element. Okay, which product is stable under which state. Okay, so that is why the correct answer will be the stability of different oxidation state. Okay. Answer question number 8. In the Pourbaix diagram, which of the following condition typically indicates that the region where a metal is thermodynamic stable and it will not corrode? Okay. So, under which condition we say that the metal is stable and it won't corrode? In general. So right now we are not talking about like iron, nickel, copper, anything. Not, like not a specific metal, but in general, which region will indicate that it a metal will be stable?
High pH value, sir.
Can anyone else tell the answer?
If concrete is having a high pH value, then steel will be more stable.
I am not talking right now about steel. I am talking in general any metal. Not even concrete I am talking about. In general any metal. It can be copper, nickel, iron, aluminium, zinc, anything. Okay, so the correct answer yes will be C. Okay, so if a metal is in elemental form, then that region will represent that the metal is thermodynamically stable. Okay, so we have seen here, like you can see here for iron, a metal is in stable state when it is in its elemental form. Okay, so that is why for nickel also we have seen the same thing, Ni metal. Okay, so this is in elemental form. So when the atom a metal is in its elemental form, then we say that the metal is thermodynamically stable and it won't corrode. When the metal it is in oxidized state, then we say that it is in the corroding environment. Okay, now question number 9. Which of the following statements is true regarding Pourbaix diagram of iron? So now we are talking specifically about iron. So I will just paste the Pourbaix diagram of iron so that you can find it easy to answer. Okay, so this is the Pourbaix diagram of iron. Now s- with this figure in your site, try to choose the correct option. Any answer I see? No, not right now. Okay, let me tell you the answer so that we can move ahead quickly. So, the correct answer for this will be C. So, you can see here from the pore base diagram, iron forms Fe2 plus and Fe3 plus in acidic condition. So, you can see in this acidic condition, there is formation of Fe2 plus and Fe3 plus state which leads to corrosion. So that's why see we say as pH of concrete decreases, the probability of corrosion also increases. Okay, so that we can see from the pore base diagram of iron also. In high alkyl condition, iron exists in Fe3 plus state, so we can see no, it doesn't exist. Iron is mostly stable in its metallic form in all pH values, so though it is stable in metallic form in all the pH range, but it depends upon the potential also, not irrespective of potential. Okay, and the corrosion of iron is dependent upon the pH, not independent of the pH. So all other statements are incorrect. The statement will be right. Okay, so let's move ahead now. So the electrochemical parameter that we discussed right now, that was electrode potential. It talks mostly about the thermodynamics, or we can say the possibility of a corrosion reaction to occur. However, for a corroding system, what matters to us the most is the rate of corrosion, that is represented using kinetics of corrosion. Okay, so the kinetics of corrosion reaction, it is represented using Butler-Volmer equation. Okay, so this is an equation that were derived by two scientists, which help us to understand the kinetics of corrosion. Now, what does this Butler-Volmer equation says? So it describes how electrical current through an electrode depends upon the voltage difference between the electrode and the bulk electrolyte for a simple unimolecular redox reaction, considering that both anodic and cathodic reaction are happening on the same electrode. So this is my electrode, which is my steel. Okay, there is anodic reaction happening here and cathodic reaction happening here, and there is a certain potential voltage difference between my electrode and my electrolyte. Okay, so based on knowing this certain potential difference that is there, that is electrode potential that we estimated earlier, how much electrical current will flow, that is what is defined by Butler-Volmer equation. Okay, so this equation is derived using four key relationships. So first is the Nernst equation that we have already seen, Nernst relation. Second is the Arrhenius equation that defines the rate of a reaction and it dependence on the free energy of the reaction. Third is the rate of a reaction. This is reaction coefficient and this is reaction rate, which is nothing but reaction coefficient times the concentration of product. And fourth is the rate of a chemical reaction, electrochemical reaction, which represents the rate of reaction relationship with the current that is flowing. Okay, these are four key relationships that are used to derive the Butler formal equation. Okay, so if I consider a simple electrochemical reaction where oxidized form is reducing into a, like suppose O2 is reducing into OH minus or Fe2 plus is converting into Fe2. So if I consider a simple electrochemical reaction like this, then initially at equilibrium, what will happen? Both forward reaction and backward reaction can happen at a same rate. So Butler-Ulmer equation, it represents I is equal to I oxidation will be equal to I reduction will be equal to I naught. Okay, equilibrium current, which is nothing but NFA e to the power minus NF E naught upon RT. So if you see delta G and minus NFE is placed here, okay, then K, instead of K I will keep this equation here. Okay, so and instead of R I will keep this equation Kc, so I will get I in terms of these relationship. Okay, so just substituting these relationship in one another, I get this equation, which is for equilibrium right now. Okay, and this diagram, it represents how equilibrium condition appears. So this is my oxidation product, this is my reduction product, and there is right now equal probability for a reaction to both oxidize and reduce. So that's why this distance is equal in both the cases, and this activation energy is also equal for both forward and backward reaction. Okay. Now, suppose I apply some external potential excitation to the system. Okay. So my system is in equilibrium. Okay. It has a potential E naught. Okay. But I am applying some external potential E. I am creating some potential difference externally to the system. So what will happen? Suppose I apply a positive potential. What will happen? My reaction will try to undergo in the backward side. It will try to undergo oxidation if I apply some positive potential. So in positive potential, I will apply. What will happen? My electrons will move away. My electron concentration will decrease. So my reaction will move towards the backward direction. Okay. Now for this to occur, oxidation to occur, my delta G should be negative. So delta G is less than delta Ga naught. Okay. So I can write it like this equation. And for reduction to not happen, delta Gc should be greater than delta Gc naught. So it will be written by this equation. And here alpha and alpha naught represents the activity coefficient. So this is my alpha and this is my alpha naught. Now since my oxidation is more spontaneous, okay, alpha will be lower. Okay, the transfer coefficient that defines the ability of a reactant to undergo oxidation or reduction, it will be lower for oxidation, so that oxidation is preferred over reduction. Okay, So there will be now net current that will exist in the system, since both oxidation and reduction is not happening at a equal rate. So I net I can write as I oxidation minus I reduction, that is nothing but NF into R oxidation minus R reduction, the rate of oxidation reaction minus rate of reduction reaction. So using the same relationship that we derived earlier, I will write it for both oxidation and reduction, and I will get this final equation. Okay, where this neta is the positive potential that we have applied to the system, which is also known as permutation. Okay, so you can see here neta is the over potential applied, and this relationship between current density and over potential, incorporating kinetics of both forward and backward reaction, this reaction is known as relationship is known as Butler-Volmer equation. So now we can predict the current that is flowing in the system when there is a certain potential that is present in the system. Okay, so system is Butler-Volmer's equation. Okay, so here this part, uh, this thing, it is represented by 1 by beta a, because it will be a constant term, and this is written as 1 by beta c, and this beta and beta c, these are nothing but Taffel's constant. Okay, so this scientist, he took this Butler-Volmer equation forward and defined some certain constant in the equation in the terms of beta and beta c, and neta is the over potential that we are applying. Okay, now there can be two types of over potential that we are applying. Suppose we have applied a very high polarization. Over potential or polarization, they are representing the same thing, neta. So suppose neta is very, very, very greater than 0. So what will happen? This second term that you see, it is nothing but 1 upon e to the power minus neta a, neta c upon beta c. Okay, so if my neta is very, very high, so it will be e to the power minus infinity, which will lead to 0. Okay, so net current will be just due to this first term. Okay, so you can see here, that is what we have written. If neta is greater than 0, then I naught will be equal to, I net will be equal to I naught times e to the power neta a upon beta a. Okay, because second term will become equal to 0, and rearranging this equation, we can get the value of beta a in terms of neta a. And if this n neta is very, very, very negative, then the same thing will happen. This first term will become equal to 0, and this term will dominate. So I can get the beta c value if I know the neta c that I have applied. Okay, so this kind of relationship that is derived when I apply a very high polarization in either positive direction or negative direction, these are known as Taffel's extrapolation. Okay, so you can see here, this is the original equation that we got from Butler-Volmer equation, and when I apply neta very positive, so when neta is very large in this order, so the equation becomes a like a straight line, and the slope of the straight line are nothing but this Taffel's parameter. Okay, so this is Taffel's extrapolation that helps us to get the Taffel's parameter. Okay, which defines the current versus potential relationship when there is very high permutation applied. And similarly, if I apply a very small excitation potential, then what will happen? This e to the power x, where is my cursor? This e to the power x term I can write as 1 plus x. Okay, so this comes from Taylor series expansion if you have read in mathematics. Okay, so Taylor series for a e to the power x function is written like this, and when x is very, very small, these all terms becomes equal to 0. So you can just write e to the power x as 1 plus x. So that is what we have done here. Okay, so I naught into e to the power x, so this is my x, so I have written it as 1 plus x. Okay, and similarly for the second term we have written this. Okay, so on resolving, what we'll get, I is equal to I core into this one 2.303 times neta upon beta a plus neta upon beta c, and this neta, which is nothing but delta e, and this I, which is nothing but the current due to this potential, it will help me to define the resistance. So we know R is equal to V by I. Okay, so 1 by R will be equal to I by V. Okay, so neta I have taken here downstairs. Okay, here comes the neta. So this remaining term will help me to calculate the resistance that a system offers. Okay, when there is very small polarization applied. So this relation is known as Stern-Geary equation. Okay, so these the scientists Stern-Geary, they defined this equation for a very small polarization. Okay, and what is the application of these two relationships that are defined? So they help us to uh, form what is known as Evans diagram. Okay, so this Evans diagram is nothing but a pictographical representation that describes the relationship between electrodes kinetic data versus the thermodynamics data. So you can see here, this was my original Butler-Wormel equation. Okay, from Butler-Ullmann equation, I got the Taffel's curve. Okay, and now this Taffel's curve, if I will draw for multiple electrodes, I will get what is known as the Evans diagram. Okay, so this Evans diagram is also known as mixed potential plot. So mixed potential theory explain metal corrosion as a reaction of two or more electrodes working simultaneously. So this is right now Taffel's plot for one system, like for iron converting into iron plus 2. The similar Taffel's plot I can make for a reducing species also, O2 converting into OH minus. And if I plot both the Taffel's plot on the same curve, I can get a mixed potential response. Like at what will be the equilibrium potential for these two reaction to occur. Okay, that I can derive. And that is what Evans diagrams tells us about. Okay. So for a metal immersed in an electrolyte, Evans diagram is represented by two linear lines, one representing the anodic potential and the other representing the cathodic potential. So you can see here there are two lines. So one is for anodic polarization and the second is for cathodic polarization, that we have seen earlier also from here. Okay. So this is how Evans diagram help us to understand. So you can see in terms of zinc and iron. So this is the Evans Taffel's curve that we have drawn for zinc. Okay, and this is the reaction of like suppose I place zinc in HCl. So how hydrogen ions will react on the zinc interface. So for that, these are Evans diagram. So when the reduction reaction of hydrogen interacts with the oxidation reaction of zinc, I will get the equilibrium current and the potential. Similarly, if I draw the same diagram for iron, this is the oxidation reaction for iron. This is the reaction for hydrogen on the surface of iron, and their interaction will give me the equilibrium potential and current for the system. So if you see, zinc has a more negative potential compared to iron and a lower current density compared to iron. So that's why we say zinc is nobler compared to iron. Okay, because iron has a higher corrosion current density compared to zinc. Okay, so this is what we understand from Evans diagram. We can see interaction of different metal in a specific environment, or what will happen if zinc is placed together with iron, that also we can understand. So when that condition arises, what will happen, this will become opposite, and that's why zinc shows sacrificial anodic property. Okay, so that is beyond the expectation of this course. So that plot I have not included, but I have shown a simple explanation where this kinetics is applied. Okay. Now, once I have derived the corrosion current, we can determine the rate of corrosion using Faraday's law. Okay. So the amount of any substance deposited or liberated during actors, it is proportional to the quantity of charge pass and the weight loss. So this is basic Faraday's law. Okay, mass law is directly proportional to charge pass and mass loss is directly proportional to equivalent weight. So this is the basic Faraday's law, and this we can use to estimate the corrosion rate. So corrosion rate is nothing but mass loss per unit area per unit time, and mass loss I can represent in terms of charge. Charge is nothing but I into T. Okay, so I will can convert this mass loss into corrosion rate, which is relating my rate to the current that I have estimated from kinetics. This is for uniform corrosion, and for localized corrosion, there is one more term that comes at the denominator, which is density. Okay, so this is how corrosion rate can be estimated once we know the corrosion current that is flowing in the system. Okay, now to understand the application of this uh, Tafel scan, Stern Gary relationship, corrosion rate, and everything. I have framed few numerical questions. So just give it a try. Like try to solve these numerical questions. Okay. First, try to understand what is question number 10, what all things are given, what all expressions we have discussed right now, and just try if you can get the answer. I will tell you the solution, but give it a try. And in the meantime, if anyone has any doubt regarding this kinetics part, they can ask. Okay, pore base diagram, we will explain again, sir, how this concept held to concrete technology concept. See, in concrete technology, when we talk about durability, durability concerned is with the corrosion of reinforced concrete. Now, before initiation, concrete is controlling the corrosion process, but after initiation, at what rate the rust is forming, that will govern the failure of my reinforced concrete system. So this kinetics part, it is defining after initiation, after after my chlorides has reached the steel interface, when the corrosion rust is forming, they will form at a particular rate with a particular current density. Okay, so that will help me to understand at what rate the reinforcement is corroding. And if I know the rate at which reinforcement is corroding, using some complex mathematical expressions or understanding, I can predict what at after how many years the concrete will start to crack. Okay, so that is why this part is important to understand. So these things comes under advanced concrete technology. For basic concrete technology, you just need to remember whatever problems we are seeing right now. You may not need to go in such depth in theory, but since I am working in the same direction in my PhD, I thought to like give you a brief overview of the concept. So maybe suppose later in future you may encounter again anything related to corrosion, then you will have a very basic idea about different terms that we have used today. So this is all about like electrochemical part, Evans diagram, Stern Gary relationship, Taffel's extrapolation, Butler Warmer equation, and Purvis diagram. These all is what is needed to understand corrosion kinetics and thermodynamics. Okay. Purvis
Sir, sir,
diagram.
all these theories are empirical based or are
These are
experimental based.
experimental based also. You can derive all these things experimentally. So all these plots that I'm saying, the beta A, beta C, corrosion current, these are all can be derived experimentally also. So for that, there is an instrument which is known as potentiostat. Okay, so that instrument helps us to, like, suppose I have a reinforced concrete system. So in that reinforced concrete system, I can apply a certain amount of potential difference and I can see how my reinforced concrete system is responding. So based on that response, these curves that you see here, we can form this proper curves. Actually, this curve we can form and we can estimate all these parameters. So these are experimentally proven things. Okay, so if you want to know about potentiostat and how these things are actually done, you can just search on Google. You will find a lot of content. Okay, and there was one doubt regarding pore base diagram. Okay, so if you see what do we mean by pore base diagram, so it is just representing the stability of a system. Okay, from Nernst equation, what we found a relationship between how we can predict the electrode potential, okay, of a system. Now this four base diagram, it maps the most stable electrode species as a function of pH and potential. So as per a potential value and as per a pH of the system, what all different product that can form at the metal non-metal interface, it is given by the pore base diagram. Okay, and based on the ion or the species that is existing at the interface, we can determine whether the system is in stable state, passive state, or a corroding state. Okay, so see, for nickel, if nickel is immersed in uh, acid solution, there are three possible reactions that can occur at the nickel solution interface. So these three are the reactions that I have written here. Now for all these three reactions, I can write a their corresponding Nernst equation. Okay, for this equation, Nernst equation will be like this, for this it will be like this, and for this it will be like this. Because this is not a redox reaction, so directly we will use this relation delta G is equal to minus RT ln K. Okay, so you can write it on your own. Okay, just try to write Nernst equation. Now this is E, this is concentration. Here there is no pH, so that's why this is a horizontal line. Here you can see in Nernst equation pH is also coming into account because there is a hydrogen ion which is involved. So that's why my potential is dependent upon pH here. And here it is not affected by the potential, it is just getting affected by the pH, so that's why it is a vertical line. So now I can guess which if my potential is this and my pH is this, I can predict what will be the ionic species that will exist in the system. So that is what Chlor base diagram tells me. Okay, it is the final application of Nernst equations that we are deriving. For iron, it is a bit complicated diagram because there are several oxidation states that can form upon iron reaction. Iron can exist in Fe state, Fe plus 2 state, Fe plus 3 state. Fe plus 2 can convert into Fe plus 3. Fe2O3 can form, Fe3O4 can form. So that's why there are more number of uh, equilibrium reactions that you see here. And the diagram is more complicated, but still, I reported all the equilibrium reactions here. Just try to write Nernst equation for all these reaction, and you will find this same plot that will come up of potential versus pH. Okay, so that will help you to define what system is stable in what condition. Okay, so this is pore based diagram. Okay, I will take like a pause of 2 3 minutes. Just try to answer this first question in the meantime. Okay, let's see the solution for this question now. Okay, I will take a new slide. I will remove this question from here. Okay, so what is given to us in the question? We know the polarization resistance value, okay, which is 10, which is 1000 ohm centimeter square. Okay, and we know the beta A, the Tafel constant for anodic curve, which is 0.120 millivolt per decade. So, but I am converting into volt so that my units are in the same order. So, 0.12 volt per decade it is given as beta A, and beta C value is given as zero point 0.1 volt per decade. Okay, so these things are given to us. So part A is to calculate the Stern Geary constant. Okay, so Stern Geary constant B, it is nothing but, so I will tell you that relationship. Okay, so if you see the Stern Geary relationship that we saw earlier, okay, so this value, this is what is known as Stern Geary constant. So I will just copy this complete equation. Okay, so I will paste it here. Okay, so this is what is represented as I core by B. Okay, so you see this value, this is nothing but equivalent to B. Okay, it's Stern Geary constant B. So it is nothing but B is equal to beta A times beta C. Okay, I'm just solving that inverse part upon 2.303 times beta A plus beta C. Okay, so this is what is known as Stern Geary constant. Okay, I core by B. We represent this relationship as I core by B because this is a constant thing. That is nothing but equal to 1 by B. So when you will put all the values, what you will get? Beta A times beta C to 1.12 times 0.10 divided by 2.303 times 0.12 plus 0.10. Okay, so this will give you an answer of 23.7 millivolt. Okay, so this is my Stern Geary constant. Now part B is determining the corrosion current. So this we can do easily because we know 1 upon Rp value. Okay, so this we know it is given to us. We know the beta value now, so I core we can easily estimate. So I core will be nothing but B upon Rp. So if I take this B here on the other side, so I core will be nothing but B upon Rp. So it is 23.7 millivolt divided by 1000 ohm centimeter square. Okay, so this will come out to be, if I convert millivolt into volt and then if I will do the calculation, okay, so it will be 23.7 microampere. Okay, so 23.7 into 10 to the power minus 6 ampere, so it will be 23.7 microampere per centimeter square. This will be my I core value. And finally, part C is corrosion rate. So we know the I core value in this formula. Okay, equivalent weight is it is given to us and density it is given to us. So corrosion rate, I just need to substitute all the values. Okay, so corrosion rate is nothing but 0.00327 times I core value, which is 27.3 times my equivalent weight 27.92 divided by density 7.87. Okay, so this will give you an answer of 0.275 mmPy. Okay, so this is how whatever experimentally we are deriving the data helps us to calculate the corrosion rate, the corrosion current, and the Taffel's constant. Okay, so this is how this application is done with the experimental data. Now just try to solve the question number 11 also again, the same application with just a little change. Okay, same question with just a little change. Try to do this. Any doubt in the first numerical, how I have applied the formulas? Okay, I will take a pause of a minute again so that I can let you think how the question will be solved, and then I will tell you the answer. I will just copy this formula so that it is easy for you to understand. Okay, for first question. Just give me the answer for first question. You know all the values that are needed for calculating the polarization resistance. Yes, the answer that you have calculated is almost correct. Okay, let me tell you the solution. Okay, so for A, the answer is pretty clear. You just need to use this relationship. So 1 upon RP is equal to I core times 2.303 into 1 upon beta A plus 1 upon beta C. So if I will do the inverse, RP will be nothing but equal to beta A times beta C upon 2.303 I core times beta A plus beta c. Okay, so when you will substitute, what you will get? 0.12 times 0.10 upon 2.303. I core is given to us 0.5 microampere. So into 10 to the power minus 6 also we need to do to convert it into ampere, and so all the units are in the same order into 0.12 plus 0.10. Okay, so when you will solve this equation, you will get an RP value of 47400 ohm centimeter square. Okay, so this is polarization resistance. Now part B, the current at a over potential using Butler-Warmer equations. For this you need to use Butler-Warmer equation that we have derived earlier. Okay, so you see this equation here. Okay, this equation is needed now. Okay, so you see this is my Butler-Warmer equation. Now what I need, I know it is zero point 0.5 microampere per centimeter square. Okay, e to the power alpha, alpha is given to us, alpha and 1 minus alpha both are equal to zero point 0.5. T is given to us, R is given to us, F is given to us, and T is given to us. Okay, N we can assume it as 2 if we are talking about reinforcement corrosion. Okay, and neta right now suppose n is equal to 1, that is also I am reporting here n is equal to 1. Okay, just to simplify the thing. Okay, and this neta it is given to us as 1000 plus 1000 millivolt. So what we need to do, we just need to put all the values here. So first if I calculate this constant term alpha into n into f upon rt, so what I will get, alpha is zero point 0.5, f is 96485, nf into neta upon rt. Okay, this is neta. So neta is given to us 1000 millivolts, so that is nothing but zero point 0.1 volt upon rt. So r is 0.8.314 times 298. Okay, so when you will do this calculation, this value will come out to be 1.945. Okay, so I net is equal to I naught, which is zero point 0.5 into 10 to the power minus 6 times e to the power 9.945 minus e to the power minus 1.945. Okay, so this is how I can calculate the current if I apply a 1000 millivolt potential. So upon solving this, what you will get, the answer will come out to be 3.42 microampere per centimeter square. Okay, so this is the application of Butler-Volmer equation if I know the corrosion current, or if I want to know the corrosion current. Okay, so we have used this relationship for first part and then this relationship for the second part. Now just solve this one more question. So this is a very simple question compared to other two questions. So I won't even tell you the solution for this question. I will just tell you the concept, how you can calculate the answer. Okay, just give it a try. Can anyone tell me how we can solve this question? Okay, so I will just give you a hint how to go along with this question. So you see here what we have given, anodic slope beta A is given to us, beta C is given to us, potential value is given to us, and current value is given to us. And we need to calculate the corrosion rate. But you see, we already know how corrosion rate is estimated. Okay, so what is needed to us? We just need the ICOR value that is given already to us. So all these extra data, it was not needed. It is just for confusion. Just the value that was needed, it was the ICOR value. And if you know the ICOR value, you know the equivalent weight and you know the density, so you can directly estimate the corrosion rate. Okay, so just substitute all the values here, and what you will get, corrosion rate will come out to be 0.10116 MMPY. Okay, so just give it a try on your own. Okay, just put ICOR value in this formula and just calculate the corrosion rate. Okay, so this is a very simple example of how from the bulk of the data you need to choose what data is relevant to your calculation. Okay, So this is how different numericals can be framed from the kinetics part of corrosion. Any doubts in this? Okay, let's move ahead then. Okay, so I will just try to end this corrosion part today, and then the special concrete part will start from the last live session. So last live session will completely discuss the special concrete. Okay, so if we just summarize this electrochemistry part of corrosion, we have seen that there are four steps that are present in a corrosion reaction. Okay, there is the anodic reaction half cell. Okay, where iron is converting into iron plus 2 state. Okay, then there is transfer of electron that is happening within the metal. Okay, electron is going inside the metal to the cathodic reaction half cell where oxygen is reducing into OH minus ions, and then the ion is moving in the electrolyte, and then it is reacting with either the this cation, and this anion is reacting to form the corrosion product. So there are four processes that are involved: anodic reaction half cell, transfer of electron within the metal, cathodic reaction of a half cell, and transport of ion through concrete. Okay, now the one which are highlighted in the red are the ones which can be which can be controlled. Okay, like we can slow down either the rate of the anodic reaction or the cathodic reaction or both, which will slow down the overall corrosion reaction. Or we can slow down the ionic movement that is happening through concrete, which can slow down the rate of corrosion reaction. However, we can't control the rate of electron movement that is happening inside the reinforcement. Okay, so these three reaction we can control, and for corrosion to occur, all these needs to occur. So even if I slow down one block, the entire reaction will be controlled. So probable areas where corrosion can be controlled or mitigated are these three blocks. Okay, now there are three ways to deal with corrosion then. Either I can control the cathodic reaction, by which I means I can lower the rate of cathodic reaction, which can be done by proper designing or detailing of concrete or by coating the concrete surface. So you see, what is cathodic reaction? It is the oxygen that is coming to pick up electron from the reinforcement surface. Now if I can delay this movement of oxygen that is happening, then I can delay the rate, slow down the rate of cathodic reaction. And for delaying the movement of oxygen, the interface is the concrete. So if I make a dense concrete, what will happen? The movement of ions will be reduced, so the cathodic reaction will be lowered. And if I coat the concrete surface with a particular coating, then also this oxygen movement will be hindered, so this rate of cathodic reaction will be controlled. So that comes under the part of cathodic reaction. You can see couple of examples, like here you can see coating being done on the concrete surface, okay, which can control the cathodic reaction. Now, either way, I can control the anodic reaction, which will lower down the rate of the anodic reaction. How it can be done? Using electrochemical techniques, corrosion inhibitor, and coating on reinforcement. Okay, so I have a reinforcement. Now, reinforcement is converting into Fe2 plus state. Okay, and here from the reinforcement, oxygen is taking up electrons to convert into OH minus. However, if I form a film over the reinforcement, then what will happen? These reaction won't be able to happen on the surface of the reinforcement. So what will happen? I can delay this anodic reaction to happen. Okay, so that's why I have corrosion inhibitors. So corrosion inhibitors, what they do? They form a film over the reinforcement surface, which inhibit this reaction to occur, which delay the anodic reaction. Okay, or I can provide some coating over the reinforcement which can delay the anodic reactions, like you can see here. Or there are electrochemical techniques like use of sacrificial anode. Okay, so when zinc and iron, they are placed connected together, what happens? Zinc corrodes rather than iron. So iron, this reaction, anodic reaction, it won't happen, the zinc will corrode. So that is known as sacrificial anode cathodic protection, which is also a technique to control the rate of anodic reaction. Okay, or I can use some metallurgical control method like use of special reinforcement like stainless steel. So why we say stainless steel doesn't corrode? Because it has a very stable passive layer that is there over the reinforcement surface due to higher chromium content that is present in the reinforcement. So this higher chromium content, it forms a layer of chromium oxide over the reinforcement surface, which has a very strong passivation tendency, and it takes a lot of time for stainless steel to corrode. So that is also a way, by altering the composition of steel, we can make it corrosion resistant. Okay, so these are the different ways in which we can deal with corrosion. Now, among different method, if we just focus on concrete, so this diagram of corrosion stage that we saw earlier, we saw in the initiation period that ionic diffusion happens through concrete, while during the propagation period both diffusion and cracking is affected by the concrete. Now there are four parameters that are associated with concrete which can affect these stages of corrosion: the porosity, permeability, concrete cover, quality and thickness, and the near surface property. Okay, so if we can enhance all these four property, then we can make concrete more resistive towards corrosion. How? So if you see permeability is the ability of concrete to allow fluids to pass through the pore structure. So if I have a very high permeability, ions can easily pass through concrete, corrosion can happen early. However, if I have a very low permeability through concrete, it will provide greater resistance to ion and it will delay the corrosion initiation. So this is how concrete can play a role here. And what factors can affect permeability? It is the W by C ratio, the curing, and the use of mineral admixture that we have already seen earlier. Second is the interconnected porosity. So this interconnected pores that are present inside the concrete, they create a pathway for ionic movement through cover. Okay, so if there is high interconnectivity, there will be easy diffusion of ions through concrete. So corrosion initiation will happen earlier and there will be higher rate of corrosion during propagation. Okay, so to control pore connectivity, we can control using lowering the water to cement ratio, improving the curing, or use of mineral admixture. Okay, now concrete cover. So this cover act as a first line of defense, and its quality and depth will directly influence the steel corrosion that we have already understood by now. So if I have a very poor quality cover that which has honeycombing, cracking, or lower depth, what will happen? It will provide lower resistance for the ionic movement and it will initiate corrosion early and it will lead to high corrosion rate. However, if you have a dense, well compacted cover, it can delay the initiation, it can slow down the propagation. Okay, and how I can control the cover? I can control the cover quality by using proper compaction, curing, and uh, preventing segregation and bleeding to occur in the during concreting. And final is the near surface property. So this includes application of coating or carbonation on the surface of concrete. So if there's carbonation at the surface, what will happen? It will fill up the pores in the concrete, which can delay the ionic movement to happen. And if we do some coating on the surface, so as we talked earlier in this slide, coating on the surface, it will delay the ingress of oxygen that is happening through the concrete surface, which can delay the corrosion reaction happening at the interface. Okay, and moisture content, again, if there is more moisture present, it can impact the oxidant diffusion or other ion diffusion. Okay, so initiation period, it will be influenced by the permeability, interconnectivity, carbonation, and the cover quality, and it will determine how quickly my corrosive ions are reaching the steel interface. However, propagation will depend upon the moisture availability, oxygen excess, and ionic conductivity, which will control the rate of corrosion and cracking. So this is how my concrete plays a role in controlling the corrosion process. Okay, through porosity, permeability, cover quality, and the near surface property. Okay, now just try to answer these three final questions. Okay, and then we'll end the session. So, question number 13: which of the following combination most effectively delays corrosion initiation in reinforced concrete? So, can anyone quickly answer the question? Yes, waterproofing can also help in corrosion control. How? Because if you are doing a waterproofing, you have seen in the cathodic reaction, oxygen in the presence of moisture consumes electron to form hydroxide ion, which are later on reacting with steel ions to form rust. So if I have done the waterproofing, what will happen? The ingress of water, like it, water is an essential part in that reaction which won't go inside, and with water, if I do a waterproofing, other ions will also not go, which usually goes after dissolving into water. So yes, waterproofing can also control corrosion. Okay, just give me the answer for question number 13 quickly now. Which of the following combination most effectively delays corrosion initiation? So the answer is very clear. Anyone can guess the answer? Okay, so it is a very simple question. Okay, so answer is C. Low permeability, low interconnected porosity, dense and thick cover. So if I have a low permeability and low interconnectivity, the ionic diffusion will be small, it will be slower, and dense and thick cover, it will ensure that it takes a lot of time for the ions to reach the concrete surface. And even after corrosion initiation, the crack propagation will be difficult if I have a dense concrete, because a denser concrete will have a higher strength and it will take more time for that concrete to crack. Okay, question number 14. Which method is most suitable for protecting steel reinforcement in a structure already showing corrosion? Okay, so again the answer is C. Yes, it is correct. Why? Because see, use of corrosion inhibitor or a increasing thickness of cover or using a high performance concrete, they are mostly effective when we want to delay the corrosion from happening. But for a structure which is already undergoing corrosion, okay, I can use electrochemical realkalization or cathodic protection. So as we have seen here, okay, when I connect zinc to steel, what will happen? Instead of steel getting corroding, the zinc will corrode. Okay, so it will stop the corrosion reaction that is happening at this iron surface, and instead the zinc will start to corrode. So such applications, they become more essential after the structure has started corroding. Okay. Question number 15. You are asked to evaluate a structure that has low visible damage but it is 30-year olds and near the sea. What testing strategies you will use to assess corrosion risk and which concrete property you will prioritize? So suppose you are on the site and you see there is very less damage on the structure which is very old, but it is located near the sea. So what all inspection you will carry out on that structure? So it is like a very open-ended question. Okay, there can be different response from different people. Okay, so I will just tell you the answer for this question because we don't have much time left. So generally on site, when we want to assess the structure for its corrosion potential, like what is the state of corrosion, one thing we can do is the chloride profile. Okay, so as we saw in ASTM testing, from different depth, we'll collect the chloride samples, and in laboratory, we'll form the chloride profile and we'll check the diffusion that is happening. And if the age of structure is less than the corrosion initiation time, that we can say that the corrosion has already initiated. Or we can check at the depth of the reinforcement what is the chloride concentration. If it is more than the critical chloride threshold, then again we can say that the chloride has initiated. So that is chloride profile testing. Then we can use half cell potential measurement. So as we saw earlier, half cell potential can help us to know the electrode potential of a system, and based on that electrode potential we can do a mapping whether the corrosion that is happening on the steel surface, it is active or passive. Okay, so that we can do. Or we can do permeability testing. Okay, so using a permeability meter or using a concrete core, if we collect a concrete core from the structure and we check the permeability, then we will know the durability condition of the concrete. We can assess the carbonation depth. Okay, so for this, what we will do, we will drill a hole inside the concrete surface and we'll spray phenolphthalein and we'll check up till what depth the carbonation has happened. So that will give us a measure to assess corrosion risk. Or I can do core sampling. Okay, so from core sampling we can check the cover quality and the pore structure. Okay, so that will help me to comment on the quality of my concrete and what is the porosity of my concrete and how risky it is for corrosion. Okay, so these are different testings that are used to assess concrete for damage. Okay, so this is what half cell testing looks like. So this is a half cell. Okay, this is a copper sulfate half cell. What you see here, we drill a hole in the concrete surface. We connect one end of the voltmeter to the reinforcement, and this other end is the connected to half cell. We keep it on the concrete surface, which we first moist with water, and this connection tells us the potential of the reinforcement, and based on the relative potential we have certain table that is given in IS code, which will help us to judge whether the corrosion is active or passive, that we can have a judgment. So this is also a NDT, non-destructive testing, that are usually done on a site to assess the corrosion risk. Okay, the next part is special purpose concrete. So this will start in the next session since we don't have time. Okay, so this is all for today's session. We talked about chloride induced corrosion first, and then we talked about science behind corrosion, where we understood electrochemistry in terms of Nernst equation, pore base diagram, Butler Volmer equation, and Evans diagram. And we solved few numericals to understand the application, and then we saw different corrosion protection measures, where we mostly emphasized on the role of concrete property in enhancing the corrosion resistance. Thank you.